Hi everyone, welcome to another video brought to you by Math Icon Institute. In this video, we'll be discussing how to convert a fraction to a decimal. But in the case where the resulting decimal will be a non-terminating recurring decimal. In our previous video, we said there are three types of decimal. So three types of decimals. Such there is the terminating decimal. So there is the non-terminating recurring decimal and the non-terminating non-recurring decimal. So there are three types. Non-terminating non-recurring decimal. It is non-terminating and it's also non-recurring. So examples of each are for terminating decimal 1.25, 0.3, and likes. So as the name suggests, terminating decimal it has an end. You can see 1.25, that's the end of decimal. 0.3, that's the end. 1.5, that's the end. But for a non-terminating recurring decimal, it is non-terminating, it is endless, it does not have an end, and it's also recurring. For example, 0.33333. So this decimal results from what? 1 over 3. So this 3 is unending. It repeats like that to infinity. So for that reason, it is what? It is non-termination, it is endless. And it's also recurring. You can see 3 is what? Repeating itself. Repeating itself. And there's also non-terminating, non-recurring. Non-terminating, non-recurring. So this is endless also, but it is not non-recurring. Examples are constants like pi and e. So pi is 3.142 and it's endless. Also, c is e exponential is 2.718 and it's also endless. So they are endless, they're not terminating, but they're not what? They are not recurring. And also in the previous video, we learned how to convert a fraction to a terminating decimal. I meant a fraction that will give a terminating decimal. Right? So we're left with the other two types. The non-terminating recurring decimal and the terminating and the non-terminating non-recurring decimal. The non-terminating recurring decimal and the non-terminating non-recurring decimal. Now, what to take note of is that we do not have any business with this anymore. The non-terminating non-recurring, we do not have any business with it. Why? Because we said in the last video that non-terminating non-recurring decimal is usually as a result of what? It's usually an irrational number. It's usually an irrational number. We said that. And an irrational number simply means a number you cannot express in what? In the form a over b. Meaning it's not a fraction. So, and since it's not a fraction, we do not have to focus on this. Our focus is what? Converting fractions to decimals. That's why for non-terminating non-recurring decimals, we don't have any problem with it. It's usually in constants, like e, like pi, and the likes. So, and in the last video, we've seen how to convert fractions to terminating decimals. The focus is now non-terminating recurring decimals. Because we said also that these two categories, terminating decimals and non-terminating recurring decimals, are a result of what? Rational numbers. So that is terminating decimal is a result of a what? A fraction. Also, a non-terminating recurring decimal is as a result of a fraction also. But when we now see a fraction, how can we know beforehand that this fraction will result into a non-terminating decimal or a terminating decimal? We already said the non-terminating non-recurring decimal is not a problem anymore. They are usually constant, like pi, like e, and the likes. So we have to focus now. Terminating decimal, non-terminating recurring decimal. So when I see a fraction, how can I know beforehand that this fraction will give a terminating decimal or a non-terminating recurring decimal? So there's a principle for that. So the principle is a rational number. A rational number A over B, written in its simplest form. As a terminating decimal. If and only if B equals 2 to the power m 5 to the power n, where m and n are greater than or equal to 0. So this is the principle. Now let's try to analyze it. Now, so the principle says a rational number A over B. You already see A over B. It's a rational number A over B. Written in its simplest form. Written in its simplest form means the fraction is already in its lowest term. What do you mean by lowest term? Usually you have fractions like 25 over 100. They will say reduce this fraction to its lowest term, meaning simplify completely. So we'd say 25 here 1, in 100 is 4, right? We have 1 over 4. So this is the simplest form of what? Of this fraction, 25 over 100. So this is what we mean by its simplest form, 1 over 4. Is the simplest form of what? 25 over 100. So if a rational number A over B now, written in its simplest form, that is, that has been simplified completely to its lowest form, as a terminating decimal, if and only if B equals 2 to the power m 5 to the power n, where m and n are greater than or equal to 0. So it means once we have a rational number in its simplest form, what should we look out for? Look out for the denominator. In this case, it is B, right? Denominator is B in this case. So to have a terminating decimal, if and only if this B satisfies this condition. What's the condition? Condition that 2 is power B equals 2 is power m and 5 is power n, where m and n are greater than or equals 0. That is m can have any value from 0, 1, 2, 3, 4. And also n can also have values like 0, 1, 2, 3, 4. Exactly. So the m and n can be 0 and it can be what? Greater than 0. So in the case where m and n are 0 now, b will be what? B is going to be 2 is power 0 times 5 is power 0. In the case where m and n are both 0, and that's what b equals 1. So obviously, if b should be equal to 1, the fraction a over b becomes what? It becomes a over 1, and that is what? That is a over 1, or a. So it's obviously a rational number. There's no problem with that. Now, moving forward, what this means is that if this b, the denominator b, should have any other prime factor other than 2 or 5, then decimal is non-terminating recurring. Listen carefully. If this denominator b of the rational number in its simplest form should have any other prime factor other than 2 or what? Or 5, then the result will be a non-terminating recurring decimal. What do we mean? Let's take examples to clarify that. So what this simply means is that b has what? It has 2 as one of its prime factors and also what? And also 5. Once it have any other prime factors as any other numbers as its prime factors, then it will be a non-recurring decimal. That's numbers like 3, numbers like 7, numbers like 11, like 13. Then it will be non-recurring, non-terminating recurring decimal. So let's see. For example, now, if we have 2 over 5, convert to decimal. 2 over 5 to decimal is what? Is 0.4. 0.4. You can see it's what? It's terminating. Why? Because it has 5 as its what? Denominator. Let's consider 7 over 10. No, 10 is what? 10 is 2 times 5, right? 2 times 5. It contains 2, it contains what? 5. So 7 over 10 is now what? In decimal, 0.7. In the previous videos, we explained extensively how to convert fractions to terminating decimals. So you can check the video. 0.7. So we have this. We can see that in the case where you have 5 as denominator, you have a mixture of 5 and 2 in the denominator. Terminating decimal. Okay, let's even consider 50 as the denominator. Let's say 7 over 50 as the denominator. And we know 50 is actually 2 times 5 times 5. You can see it contains only 5 and what? And 2. Can you see? 2 once and 5 twice. But the point is it has no other prime factor except from what? 2 and 5. That's the point. So let's see what it results into. 1 over 50 is actually 0.14. This is terminating decimal. So the point is, if the rational number in its simplest form has its denominator to contain only 2 and 5 as its prime factors, that is, it does not contain any other numbers like 3, 7, and the likes as its prime factors, then it must give a terminating decimal. And remember we said, take note of these points in the principle in its simplest form. That's very, very important. I'll explain what that means shortly. Let's consider this fraction. The fraction 3 over 60, for example. 3 over 60. Now, you see that 60 now. Let's express 60 in its prime factors. So, we will most likely have something like 2 times 2 times 3 times 5. 2 times 2 times 3 times 5. That's 60, right? Now, you can see that you have 2, and then you have 5 also in the number 60. But there's also 3, right? So, you might expect that this fraction will give a non-terminating recurring decimal. Why? Because it has some other numbers other than 2 and 5 in its denominator. But the case is not so. 3 over 60 is actually 0.05. So where's the problem? So the problem lies in this statement, written in its simplest form. So the condition is that you must have simplified that fraction to its lowest term. So 3 over 60 is not in its lowest term, right? So let's convert it to its lowest term. 3 here 1, 3 in 60 is 20, right? That's 1 over 20. 1 over 20 is actually the lowest form of this fraction. So before you can determine that, okay, let me check the denominator. Does it have any other numbers apart from 2 and 5? You have to reduce with the lowest term first. As you can see here, you have 3 over 60. The 60 has another prime factor, which is 3. That's why that it is a terminating decimal. But now that we've simplified to the lowest term, now we now have 1 over 20. 1 over 20 is actually 0.05. So you can see the principle still holds. Because 20 in its 5 factors is simply 2 times 2 times 5. So the principle still holds. So the principle is that for a number, for a fraction to give a terminating decimal, the denominator of the fraction must not contain any other number apart from 2 and 5. It might be a mixture of 2 and 5. Might have 3 2s and then 7 5s. But it should not be a combination of only 2 and 5. You should not have maybe 3 or 7 or some other numbers in the denominator. In that case, you have a terminating decimal. But if you use some other numbers, then you have a non-terminating recurring decimal. And let's say a case for that. If we have 4, for example, 4 over 7. 4 over 7 now is in its simplest form, right? But then the denominator contains a number other than 2 or 5, which is what? Which is 7. So said it should be 2 or 5 or a mixture of the two. But it's having 7 now. So let's see. So 4 over 7 gives what? 4 over 7 is actually 0.571428. 57128. And this is a typical non-terminating recurring decimal. You can see 2.571428, 571428. So this number is repeating itself. 571428, 571428, 571428. So number is repeating itself. Can you see? Okay. Let's have another number. Let's say we have 5 over 6. Now, 6 in its prime factors is what? It's simply 2 times 3, right? Yes, we have 2. When we said the number should contain 2 and 5 or a mixture of both. But this 6 now, 6 contains 2 and 3. So 6 already contains a number other than what? 2 and 5. So you should expect this fraction to be a non-terminating recurring decimal. And what's 5 over 6 in decimal? It is 0.8333. And the thing is endless. Can you see the thing is endless? So it is what? It is a non-terminating recurring decimal. I believe the principle is not clear. The principle is that we can know beforehand if a fraction will result in a terminating decimal or a non-terminating recurring decimal. What do we do? First thing is to make sure it's a rational number. It can be in the form A over B. After that, try to simplify the number to its lowest term. After doing that, now check the denominator of the number. Does it contain any other number other than 2 and 5? If it contains just 2 and 5, try to express that number in its 5 factors. That is, try to split it down into its 5 factors so that it contains just small numbers like 2, 5. So if the number contains a mixture of 2 and 5 only, then surely the fraction will give a terminating decimal. But if the number contains some other prime factors like 3, like 7, like 11, then to give a non-terminating recurring decimal. As you can see in the examples we have here, in the case where you have 7, it's a non-terminating recurring decimal. In the case where you have 6, because 6 contains 2 and 3, so it already has 3. So it also give us a non-terminating recurring decimal. That's the principle. And in the previous video, we learned how to convert fractions to terminating recurring decimals. And we said as for non-terminating non-recurring decimals, they were not gotten from fractions at all. So we do not have anything to do with them. Now our next focus is the third case. The third case is when you want to convert a fraction to a decimal, and that fraction will result into a non-terminating recurring decimal. How do we do that? Let's proceed. So in the third case, in case 3, is converting fractions to a non-terminating recurring decimals. We have these examples. The first one is 3 over 7. 3 over 7 convert to decimal. So what I'll simply use is the division house. So the division house, we said the numerator is the dividend, while the denominator is the divisor. And we said the result is the quotient. So in the division house, we place the dividend inside the house, then the divisor outside the house. So let's divide. 7 in 3. Since 3 is less than 7, what do? We simply write 0, then a decimal point, right? Then we now add the 0 here. 7 in 30, that's 4, right? Because the highest multiple of 7 before 30 is 28. 7 times 4, 28. 7 times 5 is 35. So after 28, you have 35. But we used to use the largest multiple of the divisor before the dividend. So we have 28 before 30. So 28 is 4. So we are using 4. 7 times 4 is 28. You subtract. 30 minus 28 is 2. Right? 7 in 2. Also, 2 is less than 7. So include 0 here. 7 in 20, that's 2. Because the highest multiple of 7 before 20 is 14. And 7 in 14 is 2. 7 times 2, 14. So you subtract. 20 minus 14, you have 6. 7 in 6 also. 6 is less than 7, so you include 0 here. 7 in 60, that's 8. 7 times 8 is 56, right? Don't bother about the remainder. So, 8. 7 times 8 is 56. 56. Subtract. So you have 4 again, right? Then 7 in 4. 4 is less than 7, right? Then include the 0 here. 7 in 40. 7 in 40 is 5, right? Or 7 times 5 is 35. So 5. 7 times 5, 35. Subtract. You have 5, right? 7 in 50. Add 0 here. 7 in 50. That's 7. Because 7 times 7 is 49. That's the highest multiple of 7, 450. 7. 7 times 7, 49. You subtract. You have 1, right? Add 0. Because 7 in 1 is smaller than 7. So you add 0 again. 7 in 10 is just 1, right? That's just 1. 7 times 1, 7. You subtract. What do you have? You have 3. You can see after all these divisions, 0.428571. You now have 3 here. And you can remember we started with 3. Go to the beginning. This is what? 3. So this is where the decimal will recur. So let's see how that will happen. Now 7 in 3 again. 3 is less than 7. So we include 0 here. So 7 in 30 also is 4. 7 times 4, 28. Subtract. You have 2, right? 7 in 2. 2 is less than 7. You add include 0. 7 in 20. That's 2, right? That's 2. 7 times 2 is 14. Subtract. 20 minus 14 is 6. Again, 7 in 6. 6 is less than 7. Include 0. 7 in 60 is now 8. 8. 7 times 8 is 56. You have 56. Subtract. What do you have? You have 4. 7 in 40 also. In 4 rather. 4 is less than 7. You now include 0. That will take first. If the dividend is less than the divisor, then you add 0 to it, right? 7 in 40, that's 5. 7 times 5, now 35. 35. You subtract. You have 5, right? 7 in 5, 5 is less than 7. You include 0. 7 in 50, that's 7 also. So 7. 7 times 7, 49. Subtract. What do you have? You have 1. 7 in 1 is less than 7. So include 0. 7 in 10 is 1. 7 times 1 is 7. Subtract. What do you have? You have 3. You can see the cycle has started to repeat itself again. We started from 3, right? From 3 here. Started from 3 here. Then after some divisions, we got to 3 here, right? To 30 again. Then after some divisions, we got to what? 30 again. Can you see? So it's called a non-terminating recurring decimal. We continue to divide for a complete year. The division will never end. Rather, this cycle will continue to repeat itself. So let's see. So you can see here, you have 4, 2, 8, 5, 7, 1, right? What do you have again? 4, 2, 8, 5, 7, 1. That is called the recurring. So this 4, 2, 8, 5, 7, 1 will continue to repeat itself. It will continue to occur. So if you continue the division from here again, what you have is 4, 2, 8, 5, 7, 1. You can try it. That's how you continue to have. So what do we now do? How do we write our quotient since it's a recurring decimal? So there are two ways of writing the quotient. There are two methods. The first method is to use the bar method. The bar method. So the bar method simply means you place a bar on those numbers that are recurring. In this case, which numbers are recurring? 4, 2, 8, 5, 7, 1. Because after every 4, 2, 8, 5, 7, 1, you have another 4, 2, 8, 5, 7, 1. You have another 4, 2, 8, 5, 7, 1. So those 6 numbers, 4, 2, 8, 5, 7, 1 is the one that is recurring. So we now place a bar. So we have 0 point, right? 0 point. So we have 0.42857 1. So we now place a bar on it. So that bar is telling us that this 428571 is a repetitive. It continues to repeat itself. It is the recurring part of this decimal. This is the first method of writing it. Second method is to use dots. So 0.428571. Then include three dots. These three dots is telling us that was also this decimal is recurring. It's endless. Right? It's endless. But in some cases, it will be better to use the first method. And I think let's see what other questions we have. In some cases, it's best to use the first method. Because in some decimals, the first part of decimal is not recurring. For example, in some decimals, we might have something like, for example, 0.3, 128, 128, 128. You can see you have a number 3 here before the repetitive part now start to repeat, right? So in this case, it's best to say 0.3128 now include your bar. So anyone that sees this already knows that it is that part 128 as repetitive. Maybe if you say 0.3128 and then you include your ellipses, then you might just think, okay, it is an endless decimal. But we do not know which part is what? Repetitive. We do not know. Some might think it is 3128 as a repetitive. Some might think it's a non-terminating, non-recurring decimal. But with this bar method, it is clear that it is what? It is a non-terminating recurring decimal. And also, it will tell us which part of the decimal is repetitive, is recurring. So the second question. One question we have is 1 over 3. 1 over 3. Also, let's place this in the division house. So the dividend inside, outside, you have the quotient. Now, I expect a question to cross your mind. What's the question? The question is, why are we not simplifying these fractions to their lowest term? That's because they are already in their lowest term. So, you simplify to the lowest term is not something you do always. You always really check, is this fraction in the lowest term? If it is in the lowest term, then you proceed to your division. So the first one is already in the lowest term. So also this. So that's why we do not have any issue with simplifying to its lowest term. So we move with our division directly. Also 3 1. 1 is less than 3, so you include 0. Then you have 0 point. 3 in 10 is 3, right? 3 times 3 is 9. That's the highest multiple of 3 you have before 10. So 3 times 3, 9. So you subtract. So you have 1. Also, 3 in 1. 1 is less than 3. So you include 0 here. 3 in 10. That's 3. 3 times 3, 9. Subtract, you have 1. 3 in 1. 1 is less than 3. Include 0. 3 in 10. That's 3. 3 times 3, 9. Subtract, you have 1. 3 in 1. 1 is less than 3. What do? You include 0. 3 in 10 is 3. So you do not need to be told that this decimal will continue to have 3, 3, 3, 3. You do not need to be told. It will continue to have what? 3, 3, 3, 3, 3. So it's also an example of a non-terminating recurring decimal. And for this decimal now, it is actually clear that 3 is what? Is the repetitive part of the decimal. Not 3, 3, 3, 3. So 3 is only that single number that is repeating itself. So we can write the quotient also in two ways. 0.3. And since 3 is the only number that is repeating itself, what do? Put the bar on 3. So it's still telling us that 3 is that part of the number that is what? Repeating itself indefinitely. 3, 3, 3, 3, 3. Second method is the dot method include three dots. But three dots is telling us that what? It's telling us that the number is endless. But like I said earlier, it is best to use the bar method. The bar method s- tells us that it is a non-terminating recurring decimal specifically. And it also tells us which part of the decimal is repetitive. That question we have 7 over 22. 7 over 22. Also, you'd see that all of these numbers we are dividing, you see that the denominator is just as we said, when we are trying to give a principle to know if a fraction will give a terminating decimal. You can see that the denominators of these fractions now, you can see 7, you can see 3, you can see 22. What happens? They include some other prime numbers other than what? 2 and 5. For that reason, they are non-terminating recurring decimals. So 7 over 22 is the next question. Division house, 7 is the dividend, 22 is the divisor. 22 is 7. 7 is smaller. So you have 0 point, right? And then you include 0 here. 22 is 70. That should be 3. Because the highest multiple of 22 before 70 is 66, right? So 22 66 is 3. 22 times 3, 66. Subtract. What do you have? You have 4, right? 22 in 4. Also 4 is smaller. So you include 0. 22 in 40. That's just 1. 22 times 1, 22. Subtract 40 minus 22. That's 18. 22 in 18. Also 18 is smaller. What do? You include 0. 22 in 180. That's 8. Right? 22 times 8. 176. That is the highest multiple of 22 before 180. So 176. And 22 in 176 is 8. So that's why I say it is 8. We will subtract 180 minus 176. That's 4. Right? 22 in 4. 4 is smaller, so include 0. 22 in 40. That's 2. 22 times 2. 22 in 40 is just 1. It's just 1. 22 times 1 is 22. You subtract. What do you have? You have 18. Then 22 in 18. 18 is smaller, so you include 0. 22 in 180. That is 8. 22 times 8, 176. Subtract. You have 4. 22 in 4. 4 is smaller, you include 0. 22 in 40. That's 1. Right? 1 remainder. 18. So you have 22 times 1, 22. You subtract. What do you have? You have 18. So you also do not need to be told that 18 is what? Is a repetitive part of the decimal in this case. You can say after we have 3, we continue to have 18, 18, 18, 18, 18, 18. 1 8, 1 8, 1 8, 1 8. Can you see? 1 8, 1 8, 1 8. Because in a decimals, when we want to put out a decimal, all those numbers after the decimal point, we do not call them together. We call them separately. So, for example, we have 2.18. Do not say 2.18. It's 2.18. So here we have, after the 3, we have 1 8, 1 8, 1 8, 1 8, 1 8. So the 1 8 here is what? Is a repetitive part of the what? Number. So how do we write the result for this? 7 over 22. Also, two methods. 7 over 22 is what? 0.318. Place the bar on what? On the 1 8. Why? The 1 8 is the repetitive part. The one that is repeating itself. So 0.3, then place bar on what? On 1 8. That's telling us that after you have 0.3, 1 8 is what? Repeating itself. 1 8, 1 8, 1 8, 1 8. And second method, which is not advisable to use, is the bar method. So the dot method, where you include dot, dot, dot. three dots. That is best for non-terminating, non-recurring decimal. For example, the value of pi. So pi is 3.1419. So because it is non-recurring, so we are working with this. So the three dots telling us that what? The value is endless. Also for e, exponential, 2.718. And including the three dots, we are very okay with that. But for recurring decimals, it is best to use what? The bar method. The bar method. Third question, we have third question. The fourth question is the fourth. 5 over 21. 5 over 21. You also see 1 has 2 prime factors, 3 and 7. For 3 and 7, you can see that those numbers, they are not what? 2 and 5. For that reason, we can be sure that it will be a recurring decimal. So 5 is the dividend, this one is the divisor. This one in 5, 5 is smaller. So you include 0 point, then you include 0. This one in 50. That's simply 2. This 1 times 2, 42. Because that's because the highest multiple of 21 before 50 is 42. Then 21 in 42 is 2. Then now go again and say 21 times 2 is 42. You now subtract. 50 minus 42, we have 8. Right? 21 in 8, 8 is smaller, so you include 0. 21 in 80 is 3. 1 times 3 is 63. Now you subtract 80 minus 63. That's 17. 1 in 17, 17 is smaller, so you include 0. 21 in 170. That's 8. Right? So 21 times 8, 168. Subtract, you have 2, right? 21 in 2 also, 2 is smaller, you include 0. So that's 20. Also, 20 is smaller than 21. So what do we do? Before we proceed, now include the 0 here. We have to now add another 0. 21 in 200, that's now 9. 21 times 9, that's 189. So you subtract. That's 11, right? 21 in 11. 11 is also smaller, right? So you include 0. 21 in 110, right? That's 5. 100 times 5 is 105. Subtract, we have 5, right? So you can see that so now 12, 1 in 5 is smaller, right? Include 0 again. This one in 50. You can see it's started from what? From 50. And now back in 50. That means this 238095 is the repetitive part of the decimal. But let's confirm. Let's confirm. Also, 1 in 50 is 2, right? This 1 times 2 is 42. Subtract, what do you have? 8. This 1 in 8, 8 is smaller, you include 0. There's 1 in 80. That's 3. So 1 times 3, 63. Subtract, you have 17. This 1 is 17. 17 is smaller than 21. What do we do? We include 0. 21 in 170 is 8. 1 times 8, 168. Subtract. What do you have? You have 2. 21 in 2, 2 is smaller. What do? You include what? 0. Also, 20 is smaller than 21, so you add 0 here before you now add another 0. 21 in 200, you now have 9, right? 21 times 9, you now have 189. You subtract. What do you have? 11. So 11, 11 is smaller than 21. What do? You add 0. 21 in 110 now have 5, right? 21 times 5, you have 105. Subtract, you have 5. 21 in 5, 5 is smaller than 21, right? Now include 0. Now 21 in 50. This is where exactly we started. At what? At 50. Can you see? This is 50. After some times, we got to 50. After some times, we go to what? 50. Can you see? Now let's say each part is repetitive. You can see we have 238095. 238095. So that means if you continue, we also have 238095. So it's a non-terminating recurring decimal. So how do we write the result? So 5 over 21. So the quotient is now 0.238095. And now place bar. Why? Because it is this part 238095 that is repetitive, that is repeating over time. So just place the bar on the whole of that number 238095. So we know it is that part that is what repeating itself. That's the answer. So the last question, 7 over 24. So that's an exercise for you. Divide this and tell us the answer in the comment section. Thank you.